My name's Dave. I like a bit of interaction. Thanks very much. Keep it up. And I'm going to be teaching you your first programming course here at Chalmers and Gothenburg University, Introduction to Functional Programming. I think it's going to be quite new for most of you, even if you've done some programming before. And I hope you'll enjoy it as much as I will. There's a lot of boring stuff that you usually hear about in the first lecture, but I'd rather skip that and get on with some fun stuff. So I take it you've all read this now, so you all know your first task. Find your way around the home page. Lots of material there, video links, deadlines for your labs, all sorts of information. Check it out. If you think there's something missing, you're still puzzled about anything, just post a message on the course Google group. We'll answer it as soon as we can. Otherwise, I think we should start talking about programming and programming in Haskell. So where are you going to begin when you start programming in Haskell? Well, you're going to begin at one of these boring things here, this little blue window here. It might not necessarily be blue. It might be some other color. But this is a terminal window. Some of you might not have seen one before. You can get one on most computers. It allows you to type commands. And the command that I'm interested in typing at this terminal window is ghci. That's the glorious Haskell compiler interpreter, if you really must know. It's going to give us a way of developing and viewing the results of our programming so far. So what does it look like? Well, it's not terribly exciting. I'm going to just make this a little bit darker over here so that you can sleep a little bit better if you're feeling like you need a nap. It's actually waiting for me to type something. So at the moment, we could type some things. And it's, at the moment, really just a glorified calculator. It knows about a bunch of functions. And it can use those functions to calculate things. Here's an example of a function. Adding things together. Okay? It's not very interesting, of course, but at the moment, we're just using the functions that are built in to Haskell. Now, functional programming, surprisingly, is all about functions. We're going to build programs that are described as functions. And this is functions in the sense of mathematics. In mathematics, a function is something which takes arguments and gives you a result. And it's a relation between those arguments and results that it has a special property that for any argument, there's a single result that the function gives you. Not several different results, not a different result on Monday than it does on Tuesday. So functions in Haskell are functions in that sense. So some functions are written in between their arguments, like this one, and that's sometimes called an operator, but it's just a function. Let me show you another function. I wonder if you can guess what it does. You can probably guess. It reverses things. And in the thing that I happen to have given it this time is something called a string, a bit of text. It's called a string in computer jargon. It's just a bit of text. So reverse is another function that's built in to Haskell that Haskell already knows about, or the interpreter already knows about. That's great. Anything else unusual about that? Well, you notice that in sort of normal mathematics, when you write a function and you write its argument, you put these nice brackets around it. You remember that? You know, we could do that if we really wanted to. And it wouldn't sort of make a lot of difference, but that's unnecessary. So we don't need to put brackets around arguments. Usually, sometimes. What do you think this will do? Anybody like to hazard a guess? I'm reversing hello, and I'm reversing it again. This is what happens. Oh my goodness me. Okay, so there's an error. I've typed something that doesn't make sense to the Haskell interpreter. It's saying something's gone wrong. Now, there's a lot of information that comes along with that, and you're not expected to be able to understand that information at this stage. Error messages are not going to be super helpful. You're going to have to learn to pick out the most important part of the error messages at this stage of the course. And at this stage of the course, the important part of this error message is the word error on line, line number 1, character 4. Oh, line number 4, character 1. Oh, I don't even know what that means. So what went wrong here? Well, actually, the way we would really have to write this, if we want Haskell to understand it, is that what we want to do is apply reverse to the reverse of hello. And sometimes, you see, we do need brackets. Here we need brackets because we need to tell this reverse over here that it's applied to the whole of this and not just reverse. We're not applying reverse to the function reverse. We're applying reverse to reverse of hello. And then indeed we get what you would expect. If you reverse something twice, you get back to where you started. Okay, life's going to get very boring if I stand here and just type in things that Haskell knows about and put them together. Things only really get interesting when we start to define our own functions and make our own definitions. Okay, it's not just functions. There are a few other things we define as well. But that's really how we build up programs. We build up programs by making definitions and then putting those definitions together to make more definitions. And there will be some definition of interest which will actually compute our program, the thing that we're interested in computing. Okay. Now, Haskell is a general purpose programming language. It's not a programming language for doing mathematics. But a number of the examples that we'll do in the early stages of the course will be of a mathematical flavor because everybody studied a bit of high school mathematics. So we all know a little bit of mathematics. So we use that as a kind of familiar touchstone. But don't get the impression that this is a mathematical programming language. It's a programming language that does things in a mathematical style, but it's a general purpose programming language. Okay, so if the only thing we can do here is play around with functions that are already defined, how do we define new functions and get to use them? Well, to do that, we need to use an editor to create a file containing our definitions, our program. The kind of editor we're using is not going to be Microsoft Word or PowerPoint or something like that. It's something that is used to editing files of the simplest kind, files that just contain text, usually called a text editor. Many of you may have come across them, but many of you won't have had need to edit something as simple as a text document. So you will typically have used word processors. So that's something you'll have to get familiar with. The exact editor you use is not very important, but it does help that the editor does know something about editing things written in programming languages. So you will see examples in the documentation of editors that you might want to try out on the student computers or editors that you might want to install on your own computer. So I'm going to use an editor that I always use. I wouldn't particularly recommend it because it's kind of a bit weird, but this is an editor called Aquamax, and here I've got a text file that I've called 1a.hs, first lecture part A. And this actually contains a little bit of Haskell, but not very much. I want to actually get rid of all this junk here. It's something for later. So actually all this contains is comments, lines that start with 2 dashes, or lines that are in between these funny brackets here. These are all just comments. So these are the things that Haskell is going to ignore completely. So this actually doesn't contain anything yet as far as Haskell is concerned. So let's start by defining something. So the price of prawns is 270 kronas per kilo. Actually, I just made that number up. It might be a lot more than that, or it might be a lot less, who knows. Never mind. It starts with, it's an example. So let's call that the unit price. So I'm going to make a definition. It's not a definition of a function. It's something simpler than a function. It's a definition of a value. And I'm going to put a decimal point on there to sort of give Haskell a clue that I'm interested in not just whole numbers, but potentially fractional numbers, so-called floating point numbers. And I'll come back to that later. So now I have a file that contains one very exciting definition. So now over here, I'm in the same directory, the same folder that I created the file in. And so I can load that file. And so it's now loaded the definitions from that file into the interpreter. And I can use those definitions just like I use all the built-in definitions. So for example, if you've got 7 kilos of prawns and you want to know how much it costs, I can calculate that by 7 multiplied by the unit price. You notice here that multiplication is written as a star character in Haskell and indeed in most programming languages. Okay, not terribly exciting, so let's go on to the next step. We might want to do this lots of times, so it might be useful to give that operation, computing the cost of a certain number of kilos, a name. So that's a way of defining a function. So let's call it the price, I suppose. And the price is going to take one argument, which is the number of kilos you have, and the result will be the cost of that number of kilos according to the unit price. Okay? So I name the function. I'm going to call it price. It has to be a name that hasn't already been used. So price is something that hasn't been used. I couldn't call it reverse, for example. That wouldn't work so well. Then I have to give the argument of the function a name. In mathematics, it's almost always called x, right? For some reason. Here we can use whatever name we want, as long as it starts with a lowercase letter. The same goes for functions. We can use any name we want, as long as it hasn't been used before in the current context, and it starts with a lowercase letter. So I'm going to call it kr for krona. No, I'm not going to call it kr for krona because it's the price of a certain number of kilos. Let me make some comments so that I remember what I'm doing here. This is the number of krona per kilogram. So it's just a comment to remind me what this unit is. So if I have a certain number of kilograms, I'm going to calculate the unit price multiplied by that number of kilograms. So now we've defined our first function. And so if I want to use that function, well, I have to remind the interpreter over here that I've actually changed this file. So I have to do a couple of things. I have to make sure I save this file. And I have to make sure I reload this file over here. So I can do that with the :r command. This is just telling the system, reload the file that I've just edited. When I've done that, now I can use the functions that I've defined in that file. Okay? Any questions so far? I know it's painfully simple, I guess. No comments. All right. Very good. So you notice that when I'm defining things in this file, I can use the other things which are defined in this file. And what may be not so obvious is, it doesn't actually matter which order I define these things in this file, it will still work. So you don't have to define one thing first and then another. It's just, think of it as just a set of definitions. The order is not important. among the definitions. Okay? Okay, so I've already set up the next question. Suppose the price gets cheaper if you buy loads. So if you buy more than 50 kilograms, you get a discount of 75 crowns per kilogram. It's just a comment. You see that by the color. It's in brown. That's because my text editor knows about Haskell, so knows how to color it in a helpful way. Okay, from now on, I'm not going to switch between the terminal window and my editor. It's going to be a bit smoother for me to work entirely within my editor. So I'm going to do that in this case. Some editors will support this, some won't. I'm mainly doing it because it's convenient to be able to see both at the same time. So in the top window, that's the file that I'm editing. And in the bottom window, that's the equivalent of what I had in the dark blue terminal window. That's the interpreter that will allow me to try things out. Okay? All right. So how are we going to define this function? Well, we're going to need some other mechanism because this function is a bit more tricky. You might be able to work out a way of calculating this function just using arithmetic and operations you probably can guess that are included in Haskell. But that's not going to lead to a very nice definition. It'd be pretty hard to understand and even harder to work out whether we've got it right. So we're going to need a way to define a function by cases. In this case, for example, the case when we've bought less than 50 kilos, then to calculate this discounted price, we can just use the ordinary price function. But in the case when the number of kilos is more than 50 kilos, we're going to have to do something a bit more complicated. We're going to have to apply the discount and so on. Okay? So before we try and solve that problem, let's look at a simpler version of this problem, wanting to find something by cases. Let me show you a standard function. It's called abs. And abs doesn't stand for these fantastic muscles you see here. It stands for the absolute value. Okay? So in mathematics, this is usually written by taking something and putting two vertical bars around the outside of it. It means the positive part of some number. So the absolute value of 42 is 42. But maybe more interestingly, the absolute value of minus 42 is also 42. Okay? So it basically just turns a number into its negative part, its size, or its absolute value. Okay? Anybody know why I put brackets around the minus 42? I said you don't need brackets around arguments. Why did I do it for minus 42? That's right. Minus is one of these tricky beasts because it actually plays multiple roles. Sometimes it's just a way of writing down a negative number. Sometimes it's a way of negating a number. So if you give it 7, you get minus 7. X or minus x. And sometimes it's an operator that you put in between arguments, 2 minus 1. So the minus sign has so many different roles that it can easily get confused. So that's why in this special case we need brackets around here. Otherwise it thinks we're applying abs to the minus operator, or we're subtracting 42 from the function abs. However it's going to look at it, that's not going to make any sense. Okay, so how do we define this function? It's a really simple function. We could do it with arithmetic. Anybody see how you could define abs just using arithmetic? See what I mean? Abs of x, well, you could multiply x by itself and take the square root. So if it's minus something, when you multiply it by itself, it becomes positive, and you take the square root. That's a pretty clunky way of doing it. You could do it that way. But it's much easier to think of it as if the number is positive, that's the answer. But if the number is negative, we take the negative, we multiply it by minus 1. We take the negative, the negation of it. Okay? So let's define abs ourselves. And I can't use the same name because Haskell already knows about abs, so I'm going to call it abs prime. It's a function of some number n. And the way we define functions by cases is using the following notation. We write a vertical bar, and now I'm going to write the case. And the case is usually called a guard. So I'm going to write a guard that says the absolute value of n when n is greater than or equal to 0 is just n. Okay? So now I have a definition. It's not quite a complete definition, but it is a definition. I can reload that into the Haskell interpreter, and I can look at the value of, for example, the absolute value of 42. But if I take the other example that I had earlier, you'll see that my definition is not quite complete because I'll get an error, a different kind of error than the error you saw earlier. What is the important bit of this error message? That is the non-exhaustive patterns bit. And generally what that means is you haven't defined enough equations to do the job you want to. And I haven't defined enough equations because I've only defined the equation that tells me what to do when n is greater than or equal to 0. I haven't said what I should do when n is less than 0. So I do that by adding a further guard to this definition. If n is less than 0, then the answer should be minus n. Here I'm using the minus as a function, which will give us the negative of n in the case when n is already negative. Okay, save that file, reload it, and now you see we should be able to, it should work as fine. Any questions about the first example of definition by cases? So in order to build that definition by cases, I snuck in a whole new Haskell type. We've seen that Haskell can deal with numbers, and we've seen an example where Haskell can deal with strings. That is to say, text. So strings are just the way we refer to text when we reversed hello. In fact, there's also another kind of Haskell value, which is not a number or a string. It's the result of this expression here. It's the result of doing something like, is 42 less than 0? Is 42 less than 0? The answer is not no, though. The answer is false. So these are what are called Boolean expressions, named after a mathematician, George Boole, who played around with truth and the logic of truth values. So this is a perfectly valid Haskell expression, but it doesn't compute a number, it doesn't compute a string, it computes a truth value, what we call bool. And in this case it computes false, and the other truth value, not too surprisingly, is true. And I must try not to kick the buttons at the bottom of the projector. Sorry about that. And so we saw another operator which gives us a truth value. We saw less than, n is less than 0. And we saw this one, which I pronounced as greater than or equal to. So 1 is greater than 1. Does that give me true or false? False. But 1 is greater than or equal to 1 gives me true. And there are a few other operators that you might need fairly early on. For example, equality. When are two things equal? Is 2 equal to 2.0? It is. Just two ways of writing the same thing. So there's a bunch of different operators for combining things together that give you a truth value. There are even operators that combine truth values together to give you truth values. Can anybody think of one that you might find useful in life? Yes. And or. So the logical operators. The logical operators allow you to combine truth values together. But of course, these are not very interesting things to compute on their own. They would more likely appear when we want to combine things like does that give us true or false? How many people say true? How many people say false? It's true. Unit price is indeed less than 300 and it's bigger than 10. So it allows us to build complex truth-valued expressions, Boolean expressions, from simpler ones. That's cool. Another one you might like to play around with is or, and it's written as two vertical bars. So this is a way of saying this will give us true if at least one of its two arguments is true, the left hand or the right hand one. So this one in particular will give us true. Okay, that was a little diversion. We talked about truth-valued expressions, Booleans. And why did we do that? Well, we need those in order to define guards. Guards are these things here, which allow us to define functions by cases, case by case. That's great. Why did we want to do that? Well, we had a problem to solve, so let's get back to it. And that was this one here. We had a discounted price. So let's define a new function, price2, which is the price including the discount. And then I'm going to actually build it up in some smaller steps. So let me start by defining the discount price. And this is the price for the bits that you buy over 50 kilos. Okay? So if you buy over 50 kilos, it's not the unit price anymore, it's the discount price. Now, I don't have to define all these little things here, but it's going to make my program a lot easier to understand. So what's the discount price? Is the unit price minus the discount, where the discount is going to be, what was the discount? 75 krona per kilogram. Okay. Now, why have I done this? Let me line these all up, because you can put as much space in here as you like, and so it's quite common to do this. So why have I defined it this way? Well, I've defined it this way because if somebody changes their mind about how much a kilo of prawns should cost, or how much the discount should be, then there's only one place in my file, in my script, as it's sometimes called, that I'll need to change. If I just write these numbers everywhere I need them, in 10 different places, and they have to be changed, I have to remember to change them all. But if there happens to be a use of a number, like this number here, just happens coincidentally to be the same, if I change that, my program won't work properly. Or if I forget to change one, it might not work properly. So it's a very good idea to give names to logical things, logical pieces of your program. It makes it easier to understand the program. It makes it easier to modify the program. Okay, so what's the discounted price? So this is the price for the discounted part. Well, that's just going to be the discounted price times the number of kilos. So I'm going to use these two functions to define my definition by cases. Okay. Let's just move this one out of the way because I can't see what I'm doing if I leave it lying around there. Okay. So let's see how much we can get on the same screen. Okay, so let's define this function price2. It's going to take a number of kilos. And in the case when the kilograms is less than or equal to 50, then the price will be the same as the original price, okay? Okay, so is everybody happy with the definition so far? Okay. In the other case, where the kilograms is greater than 50, okay, let's do something. It's not going to be quite right, but it'll give us something to discuss. Oops, sorry. Discounted price, kilograms. What do you think? That looks good? The comment here.
No, but you have makes 51 kilos, so that's not less expensive.
Yeah. So this is clearly not, this is actually not what's intended, but we'll get back to that. So this is a program actually has a bug in it. You might not have kind of spotted what the bug is, but there's something a bit odd about it. And the comment was that if you buy 50 kilos of prawns, you'll have to pay more than if you buy 51. That's clearly not what's intended when you have a discount for bulk buying. Okay? So the intention is that the discounted price applies to all the kilos above 50, not to all of the kilos. Okay? So we have a bit of work to do to get this right. But I want to talk a little bit about how we generally can go about testing programs in order to find bugs, in order to find errors in our program. I don't mean these sort of errors that where the thing won't actually be accepted by the Haskell interpreter. The Haskell interpreter has looked over the program and said, I can make sense of all your definitions. It's not promising you that your definitions are good. It's not promising you that your definitions are the ones you wanted. It's really just saying, they make sense to me. If you ask me to calculate these functions, I'll do my best job at doing that. It doesn't say that the functions are right. There are still things wrong, but they're things wrong which the Haskell interpreter can't spot. They're to do with the logic of the problem that we're trying to solve. So how do we go about testing things? Well, we could try our functions out on certain known values. If we know that the price of a certain number of kilos is a certain answer, we could test on that pair to see that we get the right answer. Okay? And that's a reasonable notion of testing in some cases. we're going to use a very specific method of testing quite a lot in this course. It's a bit specific to functional programming. It's one that works really well with functional programming and not quite as well with some other kinds of programming language. And that's called property-based testing. So we're going to do testing by defining properties that we expect to hold for the functions that we define. For example, this function should never give an answer bigger than 10. Could be a property that we want. Not for this function, but might be interesting for some function. And then we're going to test these properties automatically by getting Haskell, or I should say, somebody else's programs in Haskell, to randomly generate values for us and automatically test that the properties hold for those values. I'll give you an example of how we can do that with the help of this function. Okay, so let's define a property that is reasonable for any pricing scheme that you have, any discount pricing scheme. And I would say that a reasonable property for a discount pricing scheme, to be sort of fair on your customers, is that it should be monotonic. Oh, fancy. What does that mean? By monotonic, I mean that if you want to buy more kilos, it should always cost you more. Okay? Or put it another way, if the price increases by some amount, delta, the number of kilos you want to buy increases by some amount, delta. So if you start off with some amount and you increase the amount of kilos you want to buy, the cost must also increase. Right? Otherwise, something's strange. Otherwise, you pay less by buying more. Doesn't make sense. So I think that's a good property, not just for this pricing function, but maybe other pricing functions we might want to define later. But let's define it for this. So the convention I'm going to use, I'm going to define it as a function of some values, which is going to give me a result which is a truth value, a bool, okay? A true or false. But this is a function that I expect, if my program is correct, should always give me the value true. If it gives me the value false, then something's gone wrong. So let's define that. I've only got a few minutes, so I'll do it fairly swiftly and we'll talk about it after the break. So every function of this kind, properties that we expect to be true, I'm going to define using a particular syntax. I'm always going to write prop and then underscore and then the name of the property. And the name of the property here is a property of the price to function. And what I want to say is that the price you pay for a certain amount of kilos will never be bigger than the price you pay for a possibly larger amount of kilos. So the way I'm going to express that is I'm going to call the amount of kilos parameter kilograms, and I'm going to, instead of talking about the larger amount, I'm going to talk about the delta, the amount of increase. Delta is often the Greek letter you use in mathematics to talk about the increase or the change in something. So that's why I use delta here. So if I start with some amount of kilograms and I have some delta, then what I would like is that the price with this pricing scheme of those kilograms should be less than or equal to the price of those kilograms plus delta. So it doesn't matter what values of kilograms and what values of delta I feed in, I should always pay more if I get more, or rather, I should never pay less if I don't get less. Okay? Okay, so we're going to use this function as a property of a pricing scheme to test this guy. And I'm going to show you how to do that automatically, but I'm not going to do it until you've all had a cup of coffee or whatever it is you need in the next 15-minute break. Thank you.